Welcome to exercise 4.24, Gifted Children Part 1. Researchers investigating characteristics of gifted children collected data from schools in a large city on a random sample of 36 children who were identified as gifted children soon after they reached the age of 4. The following histogram shows the distribution of the ages in months at which the children were first successfully counted to 10, or first counted to 10 successfully. Also provided are some sample statistics which shall be rather useful for us. Okay, so we're going to do a hypothesis test here, okay? And in order to be able to do that, we need to know a few things. So first, we need to know, are the conditions of inference satisfied? So one of the first conditions that we always need to check into is independence. That's a huge condition, okay? So is independence here? Are we independent? So the data were randomly selected. So they told us it was a random sample from 36 children, right? And that definitely is going to make up less than 10% of all of the possible and gifted children out there, because Lord knows every child is gifted, right? So we pretty much got the independence taken care of. In other words, we are not changing the probability by taking too big of a sample from our population. Probability of success is going to remain fixed from one trial to the next. Normality. Okay, so do we have the normality condition? Well, it's not exactly normal, but I got to tell you, after having studied a lot of different distributions over my lifetime, that you're going to have a hard argument to base that is not normal. Okay, so that is definitely going to go for approximately normal. So we do have the normal condition approximately met. Probably ought to put those letters in the right order. Let's do that again. So there we go. Yeah, that's better. So normal, checkaroonie. So we are approximately normal. Okay, good. So got part A taken care of. Let's go take a look at part B. So on part B, they say, suppose you read online that children first count to 10 successfully when they are 32 months old on average. Perform a hypothesis test to evaluate if these data provided convincing evidence that the average age of when a gifted child first count to 10 successfully is less than the general average of 32 months. Use a significance level of 10%. Okay. All right, so we're going to have to go get some numbers. Let's go back up here for just a moment. We're going to have to remind ourselves. So we got n is equal to 36. The mean is equal to 30.69 months till they first count to 10 successfully. And we have a sample standard deviation of 4.31. We don't need the min and we don't need the max. We just need the sample size, the mean, and the standard deviation. Okay. All right, so how do we go about conducting a hypothesis test? What are our steps here? Well, the first step is we're going to go ahead and state our null and our alternate hypotheses, right? So what is the null and what is the alternate? So when we do hypothesis testing, that is always our first step. State the null and state the alternate. So what does the null say? Well, the null says that these gifted children, their average time to counting to 10 successfully is no different than it is for every other child, which is 32 months. No difference, right? The argument in favor of these gifted children is that no, they're gifted children. They take less than 32 months to learn how to count to 10. That's why they're gifted, okay? So that tells us this is going to be a left-tailed test. That's very important. So just as a quick reminder, if the inequality is pointing to the left, that is a left tail. If the inequality is pointing to the right, then that is going to be a right tail. This is a very cool way of telling which way you're going. And if it is a not equal to, then that is a two tail. All right, so let's go ahead and, now that we've got our hypotheses stated, let's go ahead and state our test statistic. So what is our test stat? So still working with the Z test statistic here. So Z is going to be equal to X bar minus mu, that's mu of the null, divided by our sample standard deviation over the square root of n, which is our standard error, okay? All right, so we're going to need a couple of those numbers. We're going to need to know what is our X bar equal to. Going to need to know what our S is equal to. Going to need to know what our N is equal to. All right, so go back and look at that table, and you'll see that x bar is equal to 30.69. Sample standard deviation was 4.31 months, and the sample size was 36. Okay, so that means that our test statistic z is going to be equal to 30.69 minus, remember this is where you get mu sub 0 right out of the null hypotheses, minus 32 divided by the sample standard deviation, which is 4.31 over the sample size, square root of that, of 36. Okay, let me go ahead and clean up all this stuff over here. Grab my eraser here. Maybe I won't grab my eraser. Come on, you. Let's go with a large eraser. Okay, well, for whatever reason, my eraser doesn't want to go away. So we'll just get everything to go away for a moment, and we'll get the calculator back up here. Okay, so we need to calculate that test statistics. So we're going to open a parentheses, and we'll go ahead and put in the mean, which is 30.69, the sample mean. That's my x bar. Subtract from that the population mean, which is 32. Then we're going to divide that by open a parentheses for the denominator, 4.31, divided by the square root of 36. Well, you could just put a 6 in there if you want to. Now, I'm on a fancy schmancy calculator, so I need to hit the right arrow to get out, and I'll close off my parentheses, and we come back with a z-score of negative 1.824. Okay, so it tells me that my z-score, or my test statistic, is negative 1.824. All right, cool beans. Okay, so now the next step, third step, that was the end of part 2 there. Third step is going to be to calculate my p-value. And then with any time we calculate a normal probability, we're going to draw a picture that makes the situation. So we're going to calculate that p-value and the distribution of z, okay, using our test statistic here. So our test statistic comes over here, it's negative 1.824, and the corresponding p-value is going to be this red shaded region right here. So that region down there, that will be my p-value. Notice this is a one-tailed test, so we only need to get that one side, okay? All right, so how do I get that calculation? Well, change back to blue here. Notice this left endpoint is going to be what? Negative E99. So I'm going to go from E99 up to negative 1.824, and that will be my left endpoint and my right endpoint that I'm going to put into the calculator. So what am I going to put into the calculator? Well, I'm going to put in normal CDF, left endpoint of negative 1 E99, right endpoint of negative 1.824, a mean of 0, and a standard deviation of 1. Okay, so let's go ahead and do that. So we'll go second distribution, go to number 2 for normal CDF, got the negative 1 E99 in there already, and then so let's put in negative 1 up to you. My calculator seems to not be happy all of a sudden. Well, damn the luck. Okay, I had to reboot it, but I got it fixed, so we're back. So let's go ahead and finish this up. So we're going to go into second, and I'm going to go into distributions, and I'm going to grab option number 2 for normal CDF. Got negative E199 in there, feeling good. So we're going to put in what? Negative 1.824 for the upper number, and then have a mean of 0 and a standard deviation of 1, and then we shall paste that command into the home screen. Now, for you mere mortals who don't have these fancy calculators, you're going to have to type all that stuff in by hand. So hit an enter, and we come back with a corresponding p-value of 0.0344, or excuse me, 41. Okay, so our corresponding p-value here, get my pen turned back on, is going to be equal to 0.0341. Okay. Excuse me. So what do we do for our decision? Okay, so that was the p-value. So now the fourth part here, get rid of our calculator here because we don't need it anymore. Excuse me, got a bit of a frog in my throat here. So now we got to make our decision. Okay, so how do we do our decision? Well, to do the decision, we have to decide how the p-value compares to the level of significance. So here's our p-value, and here's alpha, which is your LOS. All right, you need to put the appropriate inequality sign between the two. So we got our p-value is 0.0341, and they tell us right here that alpha is what? 0.10. So which of those numbers is bigger? Oh, alpha is. So the p-value is less than alpha, so whenever that happens, we reject the null hypotheses. If you're looking for some new ink this weekend, if you're looking to get something tattooed onto your forearm, a really good thing to have put on there is that if the p-value is greater than alpha, then you fail to reject HO. So that's one case. The second case is if the p-value is less than alpha, then we reject HO. Okay, all right, now there's a few more questions that they want us to do here. So it does show that we've got convincing evidence. So part C, let's switch over here to part C of this problem. Part C says interpret the p-value in context of the hypothesis and the test of the data. Okay, so now that we have got our p-value, what does it mean in context of the problem? Okay, so we're going to reject the null hypotheses, which means what? Well, we see that it would have been very unlikely to have seen 32 months as the mean age to start successfully counting to 10 in this distribution. Okay, in fact, excuse me, it would have been very unlikely to see 30.69, my bad, say that backwards, in the distribution if the mean was 32 months. So the mean value of 32 months so given, sorry, I forgot a word in there, apologize for that. Given the mean value of 32 months, the probability of getting a random sample, again, this is boilerplate, just like with confidence intervals, so of getting a random sample of 36 gifted children with an average age that count to 10 successfully is with x bar equal to 30.69 is 0.034, what did we say, 2? I forget, it was a 2 or 1. Let's go back a page here just to take a look. 4.1, there we go. So that's highly improbable, and therefore we reject the null hypotheses. Okay, so that's basically what the p-value is telling us. So being that that probability is so small, we will reject the null hypotheses. One way of thinking about the p-value, which is kind of a good way to help interpret it, was the p-value is telling you the chances of making a type 1 error given that the null was true. In other words, the chances of rejecting the null hypothesis when in fact it was true based upon our sample is equal to about 3%. And so we're willing to live with that risk. We're living to live with that probability of making a type 1 error, and therefore reject the null hypotheses. Okay, so next step. calculating 90% confidence interval for the average age at which gifted children first count to 10 successfully. Okay, so how should we do that? Well, we're going to need a few things. We're going to need to know what x bar is, we're going to need to know our z star, and we're going to need to know the standard error of the mean. Okay, so we want a 90% confidence interval, which means, if you think about that, again, we'll repeat this again for one more time, we're going to need to know two z stars, a lower value of z star and an upper value of z star, where that's 90% in the middle there, okay? So how are we going to calculate that? Well, that means there's going to be 5% down here and 5% up here, right? So to get that corresponding value of z star, we'll take I and V norm of 0.05, comma 0, comma 1. And that's going to give me back the lower one, give me the negative one. So let's go ahead and do that real quick. Let's get my calculator back up here. So go second distributions, I and V norm, which is option 3. The area is going to be 0.05. The mean is 0, standard deviation is 1. Let's paste that command. And it's negative 1.645. Let's get that calculator back here. I want that back. I can't keep these numbers in my head for more than a minute. Not even a minute, like 3 seconds, and they fall out of my head. So that's equal to what? Negative 1.645 for the lower one. So that's my lower z star. So that's the negative z star, okay, which means that the positive z star is, of course, going to be equal to 1.645. Okay, now how do I calculate a confidence interval? Well, it's x bar plus or minus that z star times the standard error of the x bars, okay? So what that means is, got to grab our numbers here, that's going to be 30.69 plus or minus 1.645 times our standard error, which we did that earlier when we did the confidence interval. It's 4.31 divided by the square root of 36. Okay, so let's do that. So come in here, let's clear everything out, and we're going to just do the lower number first. So we'll do 30.69 and then subtract from that 1.645 and then times 4.31 divided by the square root of 36. Now I could have just put a 6 in there, I realize it, but I just want to make it look like square root of 36 because that's how you're going to do it in most cases. All right, and so we get back the lower bound here, or the lower part of our confidence interval, would be 29.51. Now to get our upper one, simply come in and hit second and enter. Hit your second key and hit your enter key. And notice that replays the last command you just did. That works on all the calculators. And the newer ones, you could actually scroll up and grab it and paste it down. But every one of them will do it that way for you. And get over on top of where the negative was and just change that to a plus. And we get back 31.87. Okay, so somewhere between 29.51 and 31.87 roughly is our interval for when gifted children first start talking, or excuse me, first start counting to 10 successfully. Okay, so notice that if this had been a two-tailed test, we still would have rejected the null hypothesis. That's actually part E here, because 32 falls outside of that confidence interval. If you fall inside of the confidence interval, you fail to reject. If you fall outside of the confidence interval, you reject. Okay, now I would like to rework the last two problems one more time, but this time I want to show them to you using the calculator. Okay, so what I want to show you is that these commands that we've been typing out by hand here are actually built into the calculator. So let's do that. So to go ahead and get those, you're going to go into your stat menu and you're going to scroll over to test. And if you go over to test, you'll notice there are all sorts of things in here. There's a z-test, a t-test. We're going to talk about those very soon. There's a z-interval, there's a t-interval. We're going to talk about those, and lots of other ones in between. But for right now, we need the ones that we need to concentrate on, or the ones that we're going to need in the very near future. Well, actually, we're going to need some of them right now at this very moment. Is we're going to want this one. We're going to want that one. We're going to want that one. And we're going to want that one. Okay. The t-test ones and the t-interval ones, those are coming up next week. Okay. All right. So let's go ahead and show how they work. So let's do a z-test. So hit an enter. And we're not running it from data. We don't have raw data. What we have is summary statistics. So we're going to use our input is summary stats. And it's going to ask for us, what does the null hypothesis mean? Well, if you recall correctly, the null hypothesis said, what, 32 weeks, right? Or 32 months, excuse me. What was the standard deviation? Now notice it's looking for the population standard deviation. We will fix that very soon and be able to use the sample one when we work with the t-distribution. But for the moment, we'll put the sample one in there. So I'll put in 4.31. Put in our x bar, which was what, 30.69. Put in our sample size. Our sample size in this case was 36. And then we got to select which is our alternate hypothesis. Was it a two-tailed test? Was it a left-tailed test? Was it a right-tailed test? So you need to select which one of those it was. In our case, it was a left-tailed test. In other words, our null hypothesis was an equals and our alternate hypothesis was a less than. So what they're looking for here is, what does your alternate hypothesis say? Okay, I'm going to come down. We're not going to do a draw. We're just going to do a calculate. And notice it gave me the p-value, the test statistic, really easily, didn't it? Okay, so the calculator has basically automated all of those calculations that we just did by hand a minute ago. It did all of them for us rather quickly on the calculator. Okay, so that is pretty slick. All right, and so there are videos linked. I will be linking more of those into the problem sets that come with the textbook that show you how to do these things on the calculator. So I'm doing kind of a quick overview now. There's more of them coming up. Okay, let's go do the confidence interval. So if you go into stat, go over to test, and we want to go down and we want to get the z-interval, okay, because that's what we're using. So remember, the ones we're working with right now are 1, 2, 7, and 8. We will up the ante on those as we go, but those are the ones in particular for this assignment. It's just going to be 1 and 7. So grab 7 again. It's going to be summary stats. So let's see. The standard deviation was 4.31. The mean was 30.69, n was 36, and now we've got to set a confidence level. They wanted a 90% confidence level, so we're going to put in 0.90. We'll ask it to calculate that for us. And very quickly, it gives us back the same confidence interval that we got by hand just a few minutes ago. Okay, well, hopefully you find that helpful. Be sure and check out the links for how to use your calculator to do these things. Those will also be posted. But be also cognizant of how to do these things by hand. There's a lot of insight as to what's going on. It's not just all black box that way.